Namaste. In the previous class, we looked at the various chemical properties that aldehydes and ketones show. In today's class, we will start focusing on the chemical properties of carboxylic acids. Now, this is the structure of a carboxylic acid, RCOOH. Clear? Now, when you look at the reactions, basically, we can look at reactions based on where the bond is cleaved, whether the bond is cleaved between oxygen and hydrogen, or whether the bond is cleaved between carbon and oxygen. Clear? So depending upon where the bond is cleaved, we will have two kinds of reactions. Reactions involving cleavage of OH bond and reactions involving cleavage of C and O bond. Clear? So let's look at which are these reactions. The first one, reactions involving cleavage of the OH bond. Now, if the OH bond is cleaved, then I get H plus. RCOH will break to give us RCOO minus plus H plus. Since an H plus is given in this reaction, we call a carboxylic acid as an acid. So the first property that we will look at is acidity. Acidity can be understood or can be confirmed when you take that compound and react it with certain reagents. Now, who are these reagents? It can be either sodium, or it can be sodium hydroxide, or it can be sodium bicarbonate. So you can react the compound with any one of these. Depending upon the products that you get, you can infer whether the compound is acidic or not. Now let's take carboxylic acid. The general formula of this is RCOH. If it reacts with sodium, hydrogen gas is liberated with the formation of a sodium salt, sodium carboxylate. So what is the name of this? Sodium carboxylate. Same thing is obtained when you react it with either NaOH or NaHCO3. Only difference is what are the byproducts. In the case with NaOH, we get water as a product. In the case with sodium bicarbonate, along with water, you get carbon dioxide. So carbon dioxide gas is liberated. Clear? So these three are tests to confirm whether somebody is acidic or not. Clear? What happens when you take a carboxylic acid and dissolve it in water? Now, when a carboxylic acid is dissolved in water, it gives us a carboxylate ion and a hydronium ion. Hydronium because the H plus that is released from the carboxylic acid will combine with H2O using the lone pair on oxygen to form H3O plus, which is hydronium ion. So hydronium ion is formed. Along with that, I get RCOO minus. Clear? This is the carboxylate ion. Now, when you see a carboxylate ion here, it shows resonance. Now, why does it show resonance? Because I have a negative charge and a pi bond present at alternate positions, resulting in pi charge conjugation. Now, whenever there is conjugation, it will lead to resonance. Resonance is indicated by movement of electrons. We call that as delocalization of electrons. So electrons of the charge get shifted here. If it gets shifted here, the valency of the carbon is disturbed. One bond here, which is a pi bond, breaks and goes back onto oxygen to form the charge. That forms the resonating structure. Now, even here, you can see a pi charge conjugation, which will again lead to resonance. So the charge can go back in to form the bond, and this bond can break and go back on oxygen to form the charge, giving us this structure back. This keeps on happening. Hence, we see a double-headed arrow indicating that these two are resonating structures. Now, this is your resonance hybrid. Here, a resonance hybrid is a structure which gives us the features of all the resonating structures. So I have the negative charge was moving throughout this COO. Clear? So I can see a partial double bond that's created between carbon and both the oxygens which are there. So this ion is called as a carboxylate ion. So one thing is for sure, the moment we talk about resonance, we talk about stability. The moment there is resonance, stability is introduced. So a carboxylate ion is stabilized by resonance. Clear? So this is what happens when you take a carboxylic acid and you dissolve it in water. Clear? It gives us a carboxylate ion and a hydronium ion. This reaction is is a reversible reaction, which means it can attain equilibrium. At equilibrium, we can write a relationship for the equilibrium constant. Now, this is the relationship for the equilibrium constant. I will have the product of concentrations of products divided by the concentration of the reactants. Clear? So I have active mass of RCO minus into active mass of H plus divided by active mass of RCOH. This relationship is called as Ka. Ka is nothing but equilibrium concentration or equilibrium constant with respect to an acid. So what is Ka? Equilibrium constant with respect to an acid. Now why is this important? This is important because the Ka value will determine the strength of the acid. So different acids will have different Ka values. Depending upon the Ka values, we can indicate whether an acid is strong or mild or weak. Clear? So how do we do that? Larger the Ka values, stronger the acid. So this is what is the logic that is employed. Larger the Ka values, stronger is the acid. So Ka value is entirely dependent upon the concentration of H plus. Clear? So it is directly proportional to concentration of H plus. If the concentration of H plus is more, Ka will be more because these two are directly related. If the concentration of H plus is more, it means the acid is a strong acid. Hence, we look at this relationship. Larger the Ka values, stronger is the carboxylic acid. We usually use one more term which is called as the pKa with the P factor. Ka with a P factor. So pKa is given by minus log of Ka. So pKa is nothing but negative logarithm of Ka, just like pH. pH, it's negative logarithm of concentration of H plus. POH is negative logarithm of concentration of OH minus. Similarly, pKa is minus log of Ka. pKa and acid strength are inversely related. Clear? So which means smaller the pKa value, stronger the acid. Clear? So this is one more term that is used to indicate the strength of an acid along with Ka. In terms of Ka, acid strength is directly proportional. In terms of pKa, acid strength is inversely related. Now I want you to understand this. This is a very, very important logic, both for your PU as well as competitive. They might give you a series of compounds with their Ka values or pKa values. They might ask you which of them is the strongest acid, which of them is the weakest acid, or they'll give you a number of acids with pKa values and Ka values and ask you to arrange them according to increasing order of acidic strength or decreasing order, ascending order, descending order. The way the question can be asked is endless. Clear? So for that, you need to understand the relationship between the acid strength and the Ka value, acid strength and the pKa value. So let me just repeat for you. Strength of an acid is directly proportional to the Ka value. Greater the Ka value, stronger the acid. The strength of an acid is inversely related to pKa value, which means greater the pKa value, weaker the acid. Clear? So this is one conclusion I want you to remember for both PU as well as competitor. Now let us see how we can imply this to the various acids. Now there are a series of acids here. Clear? which are basically differing by what is the R group that is attached to COH. Clear? Each of these is differing by the R groups that are attached to COH, and corresponding pKa values are also mentioned. Now you can see a variation here. Now what did we understand in the previous slide? We said smaller the pKa value, stronger the acid. Now when I look at this list here, I can see a pKa value which is 0.70. So this is the smallest pKa value, and this is for what? Trichloroacetic acid. So I have 3 chlorine atoms attached to acetic acid. So trichloroacetic acid. Trichloroacetic acid is the strongest acid among this lot. And can we see which would be the weakest here? What would be the number? Yeah, this is the weakest acid. CH3, CH2, CH2, 1, 2, 3, 4, butanoic acid. So in this list, the strongest is trichloroacetic acid and the weakest is butanoic acid. Clear? Now we have all these acids which are differing in the pKa values. Now why do you see a difference here? This is the next concept that we'd like to understand, which is the effect of groups on acidic strength. Now effect of R groups on acidic strength. There are two kinds of groups that we already know, EWG and ERG. Now who is EWG? EWG is an electron withdrawing group. What is EWG? Electron withdrawing group. It means it is a group which pulls electrons towards itself. ERG is opposite of that, which is an electron releasing group. So as the name itself indicates, it releases electrons into the system. Clear? Towards the bond. Now what is the logic here? Whenever there is an electron withdrawing group attached to a carboxylic acid, it will increase the acid strength. Clear? What will happen in the case of ERG? Whenever there is an electron releasing group attached to a carboxylic acid, it will decrease acidic strength. Very, very important conclusion that I want you to remember. Whenever there's an electron withdrawing group attached to a carboxylic acid, it will always increase the acidic strength. Whenever there is an electron releasing group, it will decrease the acidic strength. And that is what you see in all these cases here. Now, why is trichloroacetic acid strong? Because I have 3 electron withdrawing groups that are attached, clear, to the carboxylic acid group. 3 electron withdrawing groups. So naturally it will increase the acidic strength. And what about butanoic acid? In butanoic acid, I have this propyl group which is attached to COH. In general, alkyl groups are electron releasing in nature. This is a propyl. It will release electrons into the COH. Hence, there is a decrease in acidic strength. And that is what you see in most of the other cases here as well. Clear? So here, when you look at the next one, say 1.29, now which has 1.29, 1.29 is Cl2CHCOH. Here you have 2 chlorine atoms that are present in acetic acid, dichloroacetic acid. There are 2 electron withdrawing groups, which will in turn increase the acidic strength compared to acetic acid. Now you look at acetic acid here, CH3COH. Acetic acid has a pK value of 4.75. Whereas the moment I replace one of the hydrogens of CH3, or subsequently if I keep on replacing the hydrogens with Cl or an electron withdrawing group, you see what's happening here? The acidic strength goes on increasing, or the pKa values go on reducing. So this is a very important slide for both your PU as well as competitive. You need to remember this, keep it in your mind. Whenever there is an electron withdrawing group attached to a carboxylic acid, it will increase the acidic strength. Whenever there is an electron releasing group, it will decrease the acidic strength. Clear? So same thing can be understood with all the other set of compounds which are there. This is one more slide which basically talks about what we discussed in the previous slide. Now here I've taken various acids which are differing in the number of chlorine atoms, point number one, and the position of the chlorine atoms. Now you look at the first case. This is CH3COH, acetic acid. Acetic acid has a pKa of 4.8. The moment I replace one of the hydrogens of acetic acid with Cl, look at what's happening. pKa becomes 2.9. Drastic reduction in pKa value, drastic increase in the acidic strength. What if I replace the second hydrogen with Cl? Look at what's happening to pKa. From 4.8, it jumps to 1.3, making this a even more stronger acid. What if I replace all the three hydrogens of acetic acid with Cl, which is trichloroacetic acid? pKa value is the lowest, indicating that it is the strongest. Now I want you to look at these two cases. I just want you to observe these two compounds and find out how are these two different and what is causing the difference in the pKa values. Of course, the difference is slight, 0.4 variation, but still there is a difference. So I want you to find out, look at these two compounds, find out there is a variation there. Yeah, you're able to figure out? Yes. The difference is the position of the halogen. Where is that halogen attached to? Which carbon is the halogen attached to? In the first compound here, the halogen is attached to the beta carbon. Now, who's a beta carbon? The second carbon from the functional group carbon, which is the carbonyl carbon. So this is the first carbon, which is called as the alpha carbon to the functional group carbon. This is the second carbon to the functional group, which is called as the beta carbon. So to the beta carbon, I have Cl substituted. Whereas when I look at this case, the chlorine is attached to the third carbon from the carbonyl group, clear, which is your gamma carbon. So chlorine is attached to the gamma carbon. Now the position of Cl, now in both these cases, I only have one Cl group atom, clear? So it's a monochloro derivative. That's the similarity. But what is the difference? The difference is the position of the halogen that is there. Where is the halogen position? Whether it is attached at beta, or whether it's at alpha, or whether it's at gamma, it makes a huge difference to the strength. Now you can see this here. In this example, this is my alpha carbon. So a chlorine is attached to the alpha carbon. So you look at what's happening to the strength. pKa value is 2.9. The moment the halogen is attached at beta, it becomes 4.1. The moment it is attached to gamma, it becomes 4.5. So if I keep on shifting the position of chlorine away from the carboxylic acid, its effect will reduce on the carboxylic acid group. Hence, you see reduction in the acidic nature. So this slide is a clear example that the number of halogens make a difference, or in other words, number of electron withdrawing groups make a difference to acidic strength. At the same time, the position of the electron withdrawing group 2 has a role to play in determining the acidic strength of carboxylic acids. Clear? All right. Now coming to aromatic carboxylic acids. Now this is one slide which talks about the pKa values of various aromatic carboxylic acids. So even here, we have different kinds of groups that are attached. Cl attached at ortho, attached at meta, or attached at para. Now you can also see the effect of the position. In the previous slide, we looked at alpha, beta, gamma. Here, in terms of, in the case with aromatic carboxylic acids, we will be talking about ortho, meta, and para. Clear? So you can clearly observe If the electron withdrawing group is present at the ortho position, the pK value is the lowest. If it is attached in the para position, the pK value will be the highest. So it is natural, right? It is closest to the functional group. Since it is closest to the functional group, its effect will be more on the COH than in the case of Cl attached at para. So orthochlorobenzoic acid is a stronger acid than parachlorobenzoic acid. Meta comes in between. Same thing is seen with other substituents as well. If I have a nitro group, whether it's attached at ortho or para, it makes a huge difference, or meta. Between substituents also, Cl and NO2. If it's at NO2, you look at what's happening to pK. pK if NO2 is at ortho is 2.17. pK if Cl is at ortho is 2.94, which means NO2 shows a greater effect, greater electron withdrawing effect than compared to Cl. Clear? Then coming to NH2. NH2 is an electron releasing group. Depending upon where it is positioned, clear, whether it's at ortho, meta or para, the acidic strength will vary. You can see clearly if NH2 is at ortho, pK is the highest, indicating that this is the weakest. Whereas if NH2 is at meta, it results in a stronger acid. Whereas when you look at NH2 at para, it's 4.89. You must have understood one thing here, or one thing should be there in your mind right now. Ideally speaking, when we are talking about distance, NH2 should have been, if it is in the para, then this acid should have been the strongest, right? But that's not the case. NH2 at meta will result in a stronger acid because it shows a lesser pK value. So I want you to take this as homework. Find out why meta amino benzoic acid is stronger than para amino benzoic acid, even though the distance in the case of para is longer. Clear? Got that? I want you to find the reason for that. So this slide basically tells us the nature of the group plays a role in determining the acid strength, whether it's electron withdrawing or whether it's electron releasing. In general, if it's an electron withdrawing group attached, the acidic strength will increase. If there is an electron releasing group attached, the acidic strength will decrease. Point number 2, the position of the substituents or the groups also matter. Where it is positioned in terms of alkyl, whether it is at alpha, beta, gamma positions, or whether it is at ortho, meta, or para in terms of aromatic carboxylic acids. And the number of these substituents also matter. Greater the number of electron withdrawing groups, the acidic strength will increase significantly. Lesser the number of electron withdrawing groups, naturally the acidic strength will be lower. Same thing applies to electron releasing groups as well. So this is a very, very important concept, one concept that has been asked a lot of times both in PU and competitive. So I want you to have multiple focus on this concept. To make you understand this concept better, I want you to take this as a homework. Now there are a set of compounds that are given here. Clear? Both aliphatic carboxylic acids and aromatic carboxylic acids. A set of values are also given. The homework is to match the values with the carboxylic acid. For this, you will have to apply the concept of effect of groups on acidic strength. If you really understood the concept, you will be able to write this in a jiffy. So take this slide as homework. Clear? All right. Then coming to the reactions that involve the breakage of CO bond There was only one property with respect to the breakage of OH bond, which was acidic nature. Reactions involving the cleavage of CO bond. CO bond also can be cleaved in reactions. So the first reaction is called as anhydride formation. First reaction is called anhydride formation. So let us understand what's happening in an anhydride formation. So I take two carboxylic acids, clear, and it is made to react with H2SO4, P2O5 in the presence of heat. H2SO4 is a very good dehydrating agent. So water is removed like this as shown. So here we are breaking the CO bond. Of course, you might tell me, sir, here OH bond is broken, but we are focusing on the reactions where CO bond is broken too. So here CO bond is broken, water is removed. After removal of water, you get a compound like this, CH3 COOCOCH3. This group is called as an anhydride group. Clear? So this group is called as what? It's called as anhydride. We call it as acetic anhydride, or the IUPAC name will be ethanoic anhydride. So this is anhydride formation. So how do you form the anhydride? React two carboxylic acids in the presence of sulfuric acid or P2O5 and heat. Water is eliminated. H plus is removed from the first carboxylic acid. OH minus is removed from the second carboxylic acid as water. The remaining groups combine to form an anhydride. Clear? All right. The second reaction is something that you've already studied in your chapter alcohols, phenols, esterification reaction. So I will not dig deep into this. Only thing I want you to remember, in an esterification reaction, when a carboxylic acid reacts with an alcohol, there is elimination of water. Now, how is water eliminated? OH is removed from the carboxylic acid and H plus is removed from the alcohol. Clear? So this is how it is removed. So the bond between C and O is broken in the carboxylic acid, and the subsequent combination of the two breakouts RCOR dash gives us an ester. So this reaction is called as esterification reaction. We saw this reaction extensively when we did the chapters in alcohols. We also spoke about what is something that you need to remember in this reaction. Carboxylic acid behaves like a base, and alcohol behaves like an acid. Clear? So this is something that we spoke about in the previous chapter, alcohols, as well. Reaction with PCl5, PCl3 and SOCl2. Again, these are again common reagents that you have come across in all the chapters that you have come across so far. Any compound with oxygen will tend to react with PCl5, PCl3 and SOCl2. Now what will happen? The common product, which is acyl chloride, is obtained. Acyl chloride is a common product, RCOCl. Clear? Which means OH is removed. The bond is broken between C and O. Clear? What is the only difference in each one of these is the byproducts. When you take SOCl2, you get SO2 and HCl. Clear? Remember, we came across this reaction even in alkyl halides, Darzin's process. Yeah, we came across reaction in alcohols too. This can react with PCl5, POCl3 phosphoryl chloride, and HCl is removed. And with PCl3, you need to take 3 moles of the carboxylic acid. So when you take 3 moles of the carboxylic acid, you get 3 moles of RCOCl and H3PO3 phosphorus acid. Okay, so pretty straightforward. Nothing much to understand. You can just imply whatever you studied in the previous chapters. Fourth reaction is reaction with ammonia, a carboxylic acid reacting with ammonia. Now let us understand what's happening here. When a carboxylic acid reacts with ammonia, a salt first is obtained. An ammonium salt is obtained. Because what's happening here is H plus breaks and takes away the lone pair on nitrogen. This NH3 will become NH4 plus. Clear? Ammonium ion. And what do I have as a counter ion? I have CH3COO minus, which is my acetate ion. So acetate ion and my ammonium ion come together to form an ionic compound, which is ammonium acetate. So ammonium acetate is first formed. Then when you heat it, there is removal of water. Like this, two hydrogens will take away one of the oxygen to go out as water. And what is obtained? CH3CONH2. An amide is obtained. Clear? So this is the reaction for the formation of an amide. So whenever a carboxylic acid reacts with ammonia, the first compound that is obtained is a salt, which is ammonium acetate if you take acetic acid. And this, upon heating, is dehydration to give us an amide. Same thing with benzoic acid as well. Benzoic acid plus ammonia gives ammonium benzoate, gives ammonium benzoate, which upon dehydration will give us benzamide. Clear? So benzamide is the product. This is an important reaction with ammonia. Clear? Then comes reduction. This is also something that we have seen in the previous chapter. Preparation of alcohols. We spoke about carboxylic acids. Carboxylic acids upon reduction will give the corresponding alcohol. So if I start with this acid, which is propanoic acid, because I have 1, 2, 3 carbon atoms, I will get propanol having the same number of carbon atoms. Yeah. So if I start with benzoic acid gets converted to benzyl alcohol. So COH gets converted to CH2OH. Same thing happens here as well. COH gets converted to CH2OH. Now, when you observe what's happening, both removal of oxygen as well as addition of hydrogen is seen. So for this, we need a strong reducing agent. Lithium aluminum hydride is what is used. So straightforward reduction. One thing you can see throughout our journey so far, we keep coming across reactions, similar reactions. At some stage, we see them as preparation methods. At some cases, we see the reactions as chemical properties. So more or less, you see similar reactions happening. This is an important reaction. It's called as decarboxylation reaction. The reaction is called as decarboxylation reaction. As the name itself indicates, decarboxylation is nothing but removal of carbon dioxide. So what is decarboxylation? Decarboxylation is removal of carbon dioxide. Clear? So carbon dioxide is removed. How is it removed? It's removed with the help of NaOH and CaO. So it's a mixture of NaOH and CaO. This mixture is called as soda lime. So what is this mixture called? It's called as soda lime. So carboxylic acid in the presence of soda lime will undergo decarboxylation, removal of carbon dioxide, to give the corresponding alkane. Now how is it removed? NaO will take away COONA to become Na2CO3. So NaO from sodium hydroxide and CONA from the acetate, from the salt, sodium salt, is removed as sodium carbonate. In place of CONA, who gets substituted? Hydrogen gets substituted, giving us methane. Clear? So this is what is obtained when you start with sodium acetate. Take a homework. I want you to prepare butane, and benzene. Prepare butane and benzene using decarboxylation reaction. This reaction is also called call-base electrolysis, because electrolysis is the method that is employed. Okay. So I've given you homework. I want you to prepare butane and benzene using call-base electrolysis. Make a note of the reagent as well. Soda lime is a decarboxylating agent. What is soda lime? A mixture of NaOH and CaO. This has been asked many times in both PU as well as competitive. Then we have the reaction called as halogenation. Now in specific, it is called as side chain halogenation. Now let's understand what is meant by side chain halogenation. I take a carboxylic acid here, and this carboxylic acid contains an alpha carbon. Clear? When it is made to react with halogen, red phosphorus, and then subsequent reaction with water, halogen can be either chlorine or bromine. Look at what the product is. The product is alpha halocarboxylic acid. What is the product? Alpha halocarboxylic acid. Now what has happened here? Hydrogen at the alpha position gets replaced by the halogen. So hydrogen that is attached to an alpha carbon, which is called as the alpha hydrogen, gets substituted with the halogen. Hence I get alpha halocarboxylic acid. Clear? This reaction is also called as alpha halogenation. This reaction is also called alpha halogenation. There's one more name to this reaction, which is called HVZ reaction. So this reaction is also called HVZ reaction. Clear? One more important reaction because it's a name reaction. HVZ is a full form for Hell-Volhard-Zelinsky. What is HVZ? Hell-Volhard-Zelinsky reaction. Clear? In short, HVZ reaction. Now we call this as a side chain halogenation because hydrogen from the carboxylic acid is not being replaced. It is hydrogen from the R group that is attached to carboxylic acid is being replaced, and this is specific to the alpha carbon. Alpha hydrogen is removed, give us alpha halocarboxylic acid. This takes place in the presence of red phosphorus and halogen. Upon subsequent reaction with water, you get alpha halocarboxylic acid. Reaction has one more name, HVZ reaction, or Hell-Volhard-Zelinsky reaction. Coming to the last reaction of carboxylic acids, all aromatic compounds undergo electrophilic substitution. So benzoic acid is no stranger either. Benzoic acid also undergoes electrophilic substitution. One thing that we have studied so far, whenever we talk about electrophilic substitution, we need to look at where will the electrophile go, whether will it go to ortho, meta, or para. Now, who will decide whether it goes to ortho, meta, or para? The functional group will decide based on whether it is electron releasing or whether it is electron withdrawing. If it is electron releasing, then ortho and para products are formed. If it is electron withdrawing, meta products are formed. Now, COH, similar to an aldehyde or a ketone, is an electron withdrawing group. So COH is an electron withdrawing group, which means the electron density will be high at meta position. So the products obtained will be meta. Products obtained will be meta. So the first one is nitration. The second one is bromination. So you get the nitro group substituted at the meta position and the halogen substituted at meta position. Clear? So this reaction is electrophilic substitution. Take a homework. I want you to write sulfonation, reaction for sulfonation of benzoic acid. And also find out why Friedel-Crafts reaction is not seen in carboxylic acids. So under electrophilic, we only see 3 reactions: nitration, halogenation, and sulfonation. We do not see Friedel-Crafts reaction. Find out the reason for the same. With these, we come to the end of all the chemical properties in this chapter: aldehydes, ketones, carboxylic acids. Let's look at why we study in terms of the uses. Now, what are the uses of carboxylic acids? Why should we study them? What is the role that is played by them in our day-to-day life? In fact, they are extensively used. One of the carboxylic acids, hexane dioic acid, is used in the manufacture of nylon polymer. To be more specific, nylon 6,6 polymer. You'll understand how it happens or what is the reaction when you come across the chapter called as polymers. So nylon 6,6, which is extensively used by us, nylon, is formed because of one of the starting compounds, which is a carboxylic acid, which is hexane dioic acid. Sodium benzoate, sodium salt of benzoic acid, which is called a sodium benzoate, is a very commonly used food preservative. We now know what is a food preservative. All these foodstuffs which have a longer shelf life, sodium benzoate is what is added. Esters, one of the products obtained during esterification of carboxylic acids and alcohols, is used in perfumery because of their pleasant smell. And sodium and potassium salts of fatty acids. Now, as the name itself indicates, fatty acids, these are long chain acids having a long parent chain, hence the name fatty acid. Sodium and potassium salts of fatty acids are used in the manufacture of soaps and detergents, which is again something that you'll study. in the chapter chemistry in everyday life that you would have studied before. Soaps and detergents, commonly used extensively by us on a daily basis. So this slide just basically tells us how carboxylic acids are important to us and why do we need to study them. Clear? So with this, we come to the end of this chapter: aldehydes, ketones, carboxylic acids. Until the next chapter, amines, namaste.